Okay, well, let's get started. Today we're very pleased to have Gilles Dowek talking about from the universality of mathematical truth to the interoperability of proof systems. So the floor is yours, Gilles.
Okay, thank you, David, and thank you for your invitation. Thank you for coming today. So I will try to share my slides with you.
And by the way, we do see you on the screen.
Okay, okay, perfect. So as David said, the title of my talk is From the Universality of Mathematical Truth to the Interoperability of Proof Systems. And the first idea I want to share with you is that we are once again in the middle of another crisis of the universality of mathematical truth. So first of all, what is the universality of mathematical truth? It is the idea that we all agree there is a unanimous agreement on what the truth condition of a mathematical statement is. So for instance, maybe we went together to the movies yesterday, and you did like the movie, I didn't. And this is perfectly okay. We don't have to agree on everything. And maybe you voted last week for a very conservative party or maybe for a very liberal one. And we know that it's important in a democracy that there is a variety of opinions as soon as everyone listens to the other peacefully. But mathematics are not in this way. If one of us think that pi is a transcendental number and another one think that it is an algebraic number, we cannot just say, well, it's okay, everyone has his or her own opinion. We think that there must be a common agreement on the truth condition of what a proof is. Yet this idea, although it's constitutive of the notion of mathematical truth itself, it has been constantly jeopardized through the history of mathematics. And when mathematicians disagree on the truth of some statement, we can call this moment in the history of mathematics a crisis of the universality of mathematical truth. So let me give you a couple of examples. And the first one is very old. And we can think that the discovery of the incommensurability of the diagonal on the side of a square by the Pythagorean school in the 26 centuries ago was a first crisis of this kind. So people started to disagree on the truth of this statement. There exists a number whose square is 2. And also a few centuries later, a similar crisis was created by the question that there exists a number whose square is -1. Another crisis came with the introduction of infinite series. So the idea of adding together an infinite number of numbers was already there at Zeno's time or at Archimedes' time. But it's only in the 19th century that we understood that the first of this statement is true and the second is not. Maybe closer to our times, the first crisis of mathematical truth, of the universality of mathematical truth, that was consciously analyzed as such a crisis is a crisis of the non-Euclidean geometries, where when people started to disagree on a statement such as the sum of the angles in a triangle equals the straight angle or not. And a less vocal one was the crisis created by the discovery of the axiom of choice and the independence of the axiom of choice, where mathematicians disagreed on the statement every vector space has a basis, because if you take the axiom of choice, of course, you can prove the theorem. If you don't, you cannot. And maybe the one that created the most anger and the more vivid fight was the crisis of constructivity, when people disagreed on the truth of the statement. If the union of two sets is infinite, then one of them has to be infinite. So these are just a few examples. Maybe these are the main crises. And the important point is that all these crises have been resolved. As soon as we are in the middle of such a crisis, the mathematicians try to resolve this crisis. It's true that crises happen, but it's false that mathematicians are happy with it. Each time a crisis occurs, then some mathematicians try to solve it, to resolve it. So if we look at the two first crises, the first one was the crisis of the square root of 2, the incommensurability of the diagonal of the side and the side of a square. Then this crisis was resolved by the introduction of two different notions, the notion of rational number and the notion of real number, that are different. And if you remove the word number, which is ambiguous, and you replace it with these two words, then you get a resolution of the crisis. The second one was solved in a very different way. It was in the 19th century with the introduction of the notion of limit. And then we could see an infinite sum as a limit of a sequence of finite sums. And hence, we could see that the first of these two statements here is correct, because this series has a limit while the other does not. If we move to the third crisis, the crisis of the non-Euclidean geometries, then the solution is much more interesting, because there are at least two possible solutions. The first one is to consider different spaces, and then everyone can agree that on a space of a zero curvature, the sum of the angles of a triangle equals the straight angle. But on the space of negative curvature, this is not the case. But there is another possibility to resolve this crisis, which is to consider two axiomatic geometries, E for Euclidean geometries and H for hyperbolic geometries. And then we see that the statement, the sum of the angles in a triangle equals the straight angle, is a consequence of the axioms of the theory E, but is not a consequence of the axioms of the theory H. Of course, these two ways to resolve the crisis are in a way equivalent, because we know that there is a soundness and a completeness theorem. Hence, if the spaces of zero curvature are the models of the axiomatic theory E, and the spaces of negative curvature are the models of the axiomatic theory H, then of course this is just each resolution is just a rephrasing of the other. Yet, if we take the second solution, the one that considers geometries as axiomatic theories rather as the study of different varieties or different spaces, then we have to change the definition of the truth condition. We are not anymore judging that a proposition is true in an absolute way, but we have to change this type of judgment into judgments where we judge that a proposition is a consequence of some axioms gamma. And what is true is not a proposition anymore, but it is a pair formed with a proposition and a set of axioms. So the truth condition should not be stated for the statements of geometry anymore, for the propositions of geometry, but for arbitrary sequence. And this yields a separation between the definition of the truth condition of a sequence, and this definition, we can call it the logical framework, and then the definition of the various geometries as theories that are expressed in this logical framework. And the logical framework that was given as a solution for the crisis of non-Euclidean geometries was predicate logic. And of course, predicate logic came only a century after the crisis of non-Euclidean geometries, but it's only when we had a predicate logic and when we could explain, when we could express both theories in predicate logic that the crisis has been completely resolved. These two solutions may also work for the crisis of the axiom of choice. And the first solution would be to replace the statement that every vector space has a basis with the statement that in a model of dead F with the axiom of choice, every vector space has a basis. And then we can all agree that this statement is true, whether we like or not the axiom of choice. And we also have to agree all together that in a model of a set theory, a Zermelo-Frankel set theory without the axiom of choice, it is not the case that every vector space has a basis. And the second solution would be to consider not the statement every vector space has a basis, but the statement that the judgment that this statement is a consequence of the axiom of choice. Or if you prefer, the theorem is not that every vector space has a basis anymore, but it is that the axiom of choice implies that every vector space has a basis. And this is something we can all agree on. And in this case, you can see that the first solution does not really work because the statements that we have are too far from the original formulation of the problem. If you take a random mathematician working on linear algebra, what the mathematician is interested in is the fact that a vector space has a basis or not the fact that this statement holds in a model of ZFC or in a model of ZF. Moreover, even if we were happy with these two statements, the problem of the absolute theory in which this statement should be proved remains. For instance, let's take the first statement where we say that in a model of ZFC, every vector space has a basis, and assume we want to prove this statement. Can we use or shouldn't we use the axiom of choice to prove this statement? So we don't really know in which theory we are supposed to prove this statement, such a statement. So this is why the second solution, the idea of replacing the statement every vector space has a basis by the fact that the axiom of choice implies that every vector space has a basis, has been chosen. And this paves the way to reverse mathematics, where instead of trying to prove more and more theorems, we try to prove the theorems we have with weaker and weaker hypotheses. Finally, for the last example I gave, the crisis of constructivity, we could also use the first resolution that would lead to very awkward statements, such as in a model valued in a Boolean algebra, when the union of two sets is infinite, then one of them has to be infinite. But on the fact that in a model valued in a Heyting algebra, this is not the case. And again, these statements are too far from the original formulation of the problem. And again, the question of whether we could use or not the excluded middle to prove these two statements remains. So this is why we prefer the second type of solution and say that the fact that when the union of two sets is infinite, then one of them has to be infinite is a consequence of the excluded middle. And whether or not we like the excluded middle, whether or not we want to take the excluded middle, it is a fact that this theorem is a consequence, this proposition, this statement is a consequence of the excluded middle. In fact, there is, in this particular case at least, but maybe in others, there is a third solution to a third resolution to the problem, which is now called ecumenism. We saw that we could change the axioms. For instance, we could take the excluded middle as an axiom, or we could decide not to take the excluded middle as an axiom. But when we do that, we keep the same symbols. So we keep a symbol for disjunction, for instance. We keep a symbol for negation. And with these two symbols, it is only that we decide in one case to take the axiom A or not A, the excluded middle, and that we decide not to take this axiom in the second case. But we have to remember that these axioms, they are here to express the meaning of the symbol that we use. So if we use different axioms, it means that we give a different meaning, for instance, to the disjunction. To when we say A or not A holds, or when we say that it doesn't, we change the meaning of the word or that we put between A and not A. So if we have symbols that have different meanings, we should use different symbols, just like we already use different symbols for the inclusive or and the exclusive or. And there is no fight between two communities of mathematicians, one thinking that the disjunction should be inclusive and the other thinking that the disjunction should be exclusive. Everyone agrees that we can use both or either, and they are just different notions, they are different connectives, and we should write them in a different way. So if we follow this idea, the only mistake is not to accept or to reject the excluded middle, but it is to use the same symbol for the constructive disjunction and for the classical one. And once we introduce these two notions, these two symbols, the constructive and the classical disjunction, nothing prevents from using them both in one statement. And if we do that, we have to agree on the fact that the statement that we started with, if the union of two sets is infinite, then one of them has to be infinite, is true if the implication and the disjunction are classical connectives, classical concepts, but not if they are the constructive counterparts of the same concepts. And you see that this idea, in fact, is not completely new, because when we discussed the solution of the first problem, the first crisis, the crisis of the irrationality of square root of 2, we introduced two notions, two names, two words, rational number and real number, and it was already a form of ecumenism. And in the same way, once in physics, we understood that the notion of mass and weight are different notions, we decided to use two words, and it is exactly the same thing that we are doing here with the classical and the constructive disjunction. So we see that the past crises, again, I recall the 5 crises I discussed, the irrationality of square root of 2, the infinite series, non-Euclidean geometries, the axiom of choice, and constructivism. All these crises have been resolved in a way. But the second idea I want to share with you today is that we are again in another crisis, in a, if you like, the 6th crisis of the history of mathematics. And this crisis has been triggered by the development of computerized proof systems. So computerized proof systems like Coq, Isabelle, HOL, PVS, Whole-Light, Lean, and many others are systems where a mathematician can express a mathematical proof, and the system checks the correctness of this proof. In many cases, the system also helps the mathematician to build the proof. And I think many of us agree that the development of this system is a major step forward in the quest of mathematical rigor. And as you know, through the history of mathematics, we have always been in a quest for more and more rigor in the way we state things, in the way we define things, in the way we prove things. And here we reach a new step because the proofs that we write with such a system are much more rigorous than the proof we write with a pencil and a paper. But the development of these systems jeopardizes once again the universality of mathematical truth. So why? Because before we had these systems where we were only able to write proofs with a pencil and a paper, we had, for instance, a proof of Fermat's little theorem. But since we have all these systems, now we speak of a Koch proof of Fermat's little theorem or a PVS proof of Fermat's little theorem. And we are not even sure when we have a Koch proof of Fermat's little theorem that this proof could be expressed in PVS. Of course, it is often the case, fortunately, but as Koch and PVS are different systems, there is no proof that each time we have a theorem in Koch, we have the same theorem in PVS, and there are even a few counter examples, which are very artificial examples, but we know there are things we can prove in Koch, but not in PVS, and vice versa. So we see that each of these proof systems, and maybe there are 20 or 30 proof systems of this kind today. So each proof system defines its own language for mathematical statements and its own truth conditions. And so this triggers another crisis to be resolved. So as we have already resolved 5 crises, maybe we can take an inspiration on the way these crises have been resolved, so that we understand how to resolve this one as well. And you remember that there is a solution that already worked for several crises, at least the crisis of non-Euclidean geometry, the crisis of the axiom of choice, and the crisis of constructivism. It is to express theories that are implemented in these proof systems, such as Koch, Isabelle, HOL, PVS, whole light, lead, and so on, in predicate logic. And if we are lucky, we can hope that these theories will have a lot of common axioms and a few axioms differentiating them one from another. And for instance, this is the case in geometry, where most of the axioms are the same in all geometries, and only the parallel axiom or its negation change from one geometry to another. Maybe if we are lucky, we will understand how to mix these axioms, differentiating the symbols that we use. So maybe there is a symbol which is used in Koch, let's say the constructive disjunction, which is not used in PVS, and vice versa, but we can mix these symbols in the way we did in ecumenical logic. Then we would be able to analyze which proof uses which axiom, just like we did for the axiom of choice. For instance, we know that the incomplete base theorem requires the axiom of choice, or the fact that the product of 2 compact spaces is compact requires the axiom of choice. But if you want to prove that 9 is not a prime number, you don't need the axiom of choice. And maybe we can also try to find better proofs using less axioms, just like we do when we try to constructivize a proof, that is to find another proof that does not use the excluded middle, or when we do when we look for simpler proofs or proofs using less axioms in reverse mathematics. In fact, this program doesn't work, and it doesn't work for one reason, which is that predicate logic is not the right logical framework to do that. But in fact, we could still take an inspiration on the way we have solved the previous crises in the history of mathematics, but instead of using predicate logic as we did at the beginning of the 20th century, we could use an arbitrary logical framework. And again, we can formulate a program which is to do exactly the same thing that we discussed on the previous slide, but to do that in a different logical framework from predicate logic. In fact, the history of logical frameworks is already very long, because predicate logic is almost a century old. Predicate logic has been published by Hilbert and Ackermann in 1928. So it will soon be the century of predicate logic in a few years. And during this century, several other logical frameworks have been developed, such as λ-Prolog, Isabelle, the Edinburgh logical framework, pure type system, deduction modulo theory, ecumenical logic, and the logical framework I will speak about today, which is called Deducti. So Deducti borrows many ideas from the previous logical frameworks. And if you compare what you can do in Deducti with what you can do in predicate logic, there are mainly 4 differences. The first one is that you can define symbols that bind variables in Deducti, and like in λ-Prolog, in Isabelle, or in the Edinburgh logical framework, while in predicate logic, as you probably know, function symbols and predicate symbols cannot bind variables. Only quantifiers can bind variables. The second difference is that the proofs can be expressed as terms in the logical framework, and it is the same in the Edinburgh logical framework, which is an idea we borrowed from the Edinburgh logical framework. Then we know that in modern logic, such as the calculus of construction or even higher order logic, simple type theory, proofs are not just made with deduction rules and axioms, but also with computation rules. And the idea of mixing deduction and computation in proofs comes from deduction modulo theory, but it was already there in specific formalisms such as the calculus of construction or Martin-Löf type theory. And finally, we can express in Deducti both constructive and classical proofs, like in ecumenical logic. So you see that we borrowed these ideas from all the previous logical frameworks that I mentioned. So this is what Deducti is useful for. Now let's see how Deducti is made. So Deducti is simply a typed lambda calculus with 2 features. First, it has dependent types, and then it has computation rules. And this system has been implemented. It already has several implementation, such as a decay check, which is a historical implementation, lambda pi, code check. And the idea we are trying to promote is that this system is simple enough so that postdoc should be able to develop her own implementation of Deducti in 2 weeks and a PhD student in 1 month. And in fact, we have some kind of empirical evidence that this is possible. I will not explain in details the rules, the typing rules of Deducti, but I will illustrate these 2 features, dependent types and computation rules, with examples. So when you use a logical framework, you have first to define your own theory. And only once you have defined your theory, you can check proofs that are expressed in this theory. And so there is no per se deductive proofs of anything. Each time you speak of a proof that has been checked in Deducti, it has been checked in some specific theory. And the proof is expressed not in Deducti, but in this theory, which is itself expressed in Deducti. When you define a theory in predicate logic, you have to give first a language. And defining a language amounts to define sorts, function symbols, and predicate symbols. And then you have to give a set of axioms. In Deducti, it also goes in 2 steps. You first have to give a set of symbols. And this symbol, they replace the sorts, the function symbols, the predicate symbols, and the axioms. And then you have a second step where you have to give computation rules. And again, I will show that on examples. Let us see now a few examples of axioms that we can express in Deducti. And the first axioms I will present are a way to catch up with predicate logic. And indeed, as we have seen, predicate logic is a quite sophisticated framework where you have a lot of notions. You have a notion of sort, a notion of function symbol, a notion of predicate symbol, a notion of arity, a notion of variable, a notion of term, a notion of proposition, a notion of proof. And a typed lambda calculus, such as Deducti, is much more primitive. You have much less primitive notions. And all these notions, they have to be reconstructed. So it is both a good exercise to start to catch up with predicate logic, but it is also of an interest in itself. For instance, the first book of Euclid's Elements has been formalized in Coq. And then we have been able to translate it from Coq to Deducti, but to Deducti in the theory of Coq. And then by analyzing the proofs, we understood that all the power of Coq, all the power of the calculus of inductive construction was not needed to express the proofs of Euclid's elements, the first book of Euclid's elements. And of course, we know that Euclid did not use inductive types or universes or all these very advanced features of Coq, and they could be expressed simply in predicate logic. So we had to modify a little bit the Coq proofs because some features of Coq were used in these proofs, but it was not too difficult. And eventually, we got the first book of Euclid elements expressed in a very weak theory in Deducti, which is the theory corresponding to predicate logic. And so this is a work Johan Gerand did. And once he did that, he could export this first book of Euclid element to many systems, because as soon as the system supports predicate logic, and many systems do, of course, then we can translate the deductive proof in predicate logic of the theorems in the first book of Euclid's element to this system. So let us try to do a little exercise. So if we want to define predicate logic, in predicate logic, we have two types of expressions. We have terms and propositions. And we introduce here two constants. The first one is a capital iota. So I know it looks like a capital I, but it is in fact a capital iota. A capital iota that will be the type of the terms. And another constant, which is called prop, and that will be the type of propositions. And indeed, you can guess that the function symbols will just be functions expressed with symbols of type iota, arrow, iota, arrow, iota, and returning an expression of type iota, because a function symbol takes as argument terms and returns a term. A predicate symbol, in contrast, will take as argument terms, that is, expressions of type iota, and will return a proposition, that is, an expression of type prop. And the connectives, such as conjunction, disjunction, and so on, will take as arguments propositions and return a proposition. The only non-trivial symbol here is the for all quantifier, and the existential quantifier would be the same as the universal quantifier, that has this higher type, iota arrow prop, arrow prop. And this is due to the fact that this symbol binds a variable in predicate logic, and to express this binding, and you see here how we express in general binding in Deducti. We use the so-called higher order abstract syntax that was already there in λ-Prolog and in other systems. And the proposition for all xa is expressed as for all applied to the function lambda xa, hence the type iota arrow prop, arrow prop. So you see here how we can express a symbol that bind symbols that bind in Deducti. You also see that here in this example, we have symbol declarations only. So this example is not strong enough to explain the use of computation rules. And also it is expressed in simply typed lambda calculus. So we don't use the dependent types yet, so that we will see that on the next slides. And maybe the only unusual thing is that iota and prop are not declared as types, as we would maybe in other implementations of simply typed lambda calculus, but they are declared as constants of type type. And here we have one of the keywords of Deducti, type in capital, with all the letters in capital, which is the type of all types. So this works if we want to express proofs in predicate logic with one sort. But in many cases, in particular in geometry, we want to have several sorts of terms. For instance, points, lines, circles. So imagine you want to express a theory that has three sorts, iota 1, iota 2, and iota 3. And the only thing you need to do is to declare several constants of type for the terms of type iota 1, for the terms of type iota 2, and the terms of type iota 3. But if you do that, you will then need several universal quantifiers. So, for instance, one to quantify over the variables of sort iota 1, one to quantify over the variables of sort iota 2, and one to quantify over the variables of sort iota 3. And you see that here we have almost the same type as what we had before, except that instead of having iota, we have different iota 1, iota 2, and iota 3. And this is something which is not very nice. So we want to have just one universal quantifier. We want to have a generic universal quantifier. So one way to do that, of course, would be to replace the iota 1, iota 2, and iota 3 with a type variable, x, and we will have a quantifier of type x arrow prop, but we have to give as a first argument to the quantifier the type with which we want to use the quantifier. So we will have here a function that takes first a type x, and then takes a function from this type x to prop. And you see here that the type of the second argument depends on the value of the first, and this is what we call dependent types. So here we have the first illustration of the use of dependent types in Dedukti. But this doesn't work in Dedukti for two reasons. One is a minor one. It is that we don't have a dependent product. We don't have dependent function types with type as a first argument. And it is a minor issue because we could just modify the language Dedukti so that we do allow the quantification over type variables. And we don't, but we could. But there is also a more severe restriction. It is that there are many things in type beyond iota 1, iota 2, and iota 3. And for instance, prop, as we have seen, is also a constant in type. So if we took this type for the universal quantifier, we could automatically quantify other propositional variables. So in some cases, we are very happy to quantify other propositional variables, but in some cases, we don't. And as we are not here advocating for one theory or another, but we are developing a logical framework, we have to keep some neutrality. If the theory has a quantification over proposition, then we should be able to express it. If it doesn't, we should be able to forbid it. And if we took this notion, this type for the universal quantifier, then we could not. So this is a typical way we solve this problem in Dedukti. And once you have understood that, you have understood most of what you need to understand to use Dedukti. So before we had, I'm reading the first column here. Before we had type iota. And now we are introducing another type, which is called set, and which is the type of the codes or the names of types. And just as we have a type iota, we have a type lowercase iota, which is in set. Then we have a symbol called element, EL, that is an embedding of sets into types. So it associates to each name of a type as a type itself. And here we see, for instance, that if we apply this symbol EL to the type lowercase iota, then we want to have something that is equivalent or that is the same thing as capital iota. And to express this equivalence, we introduce a computation rule that transforms every expression of the shape element of lowercase iota into a capital iota. Then we can introduce the type prop, and we can give to the universal quantifier now a slightly different type. It's almost the same as the previous one, but it's slightly different. We take a variable of type set, and then we take a function that maps the elements of X to prop. And you see here that applying this universal quantifier to lowercase iota, you get a quantifier of type iota arrow prop, which is what you wanted. But there is no name for the type prop. Hence, you cannot apply this quantifier to a name of prop that would give you a quantifier that binds over propositional variables. So by restricting the types that have a name in the type set, we can restrict the use of this universal quantifier exactly to the types that we want. Now, what should we do? And this is the right column. If we want to have three types, three sorts, iota 1, iota 2, iota 3, then we should introduce lowercase iota 1, lowercase iota 2, lowercase iota 3, and 3 rewrite rules. And again, we could then quantify over variables of type iota 1, iota 2, and iota 3, but not prop. And here we can see all the features of Deducti, because in the type of the universal quantifier, we have dependent types. And we also have several computation rules, several rewrite rules that are here to type terms, to help to type terms by identifying two types, such as element of iota 1 and capital iota 1. And this trick, if you like to call it in this way, is reminiscent of the way we express simple type theory in predicate logic, and also in universes à la Tarski as they are used in Martin-Löf type theory. So far, we have seen how to express terms and propositions of predicate logic. And now let's see how we can express proofs. And this will be the last example, almost, I will discuss before I go to the next part, which is almost the conclusion. So the first remark is that proofs are just trees, like terms and propositions are. So as any tree, as any set of trees, they can be expressed in Deducti. But we can go a little bit further and use the so-called Curry-Howard isomorphism that I call here Curry-De Bruijn-Howard, but it is exactly the same thing, which says that the proposition P implies P, for instance, should be the type of its proofs. And here in Deducti, it is not possible for the proposition P implies P to be the type of anything, because P implies P has type prop, and prop itself is a type, but P implies P is not a type, so it cannot be the type of anything. And to solve this problem, we have to introduce another embedding, which is very similar to the element embedding, but now it is a proof embedding that maps every proposition to the type of its proofs. So for instance, the expression P implies P is not a type, so it cannot be the type of anything. But the expression proof of P implies P is a type, because when you apply proof to a proposition, you get a type. And this is the type of the proofs of P implies P. And note again that exactly as we said for the previous example with the embedding element, this embedding is not surjective. There are many things in type that are not types of proofs. And for instance, the type iota or the type prop are examples of types that are not types of proofs. They are types of terms, they are types of propositions, but not types of proofs. Only the types starting with the constant proof are types of proofs of some proposition. Now, what we want, if we follow Brouwer, Heiting, and Kolmogorov's explanation of what a proof is, which is the basis of the Curry-De Bruijn-Howard isomorphism, then this explanation tells us that the identity over the proofs of P should be a proof of P implies P. A proof of an implication is a function or an algorithm that maps the proof of the antecedent to the proof of the successor. But we see here that the identity over proofs of P, so lambda x, has the type proof of P, arrow proof of P, and not the type proof of P implies P. So if we want to be able to give the type proof of P implies P to this identity function, then we have to identify the types of proof of P implies P and proof of P arrow proof of P. And to do so, we have to introduce another computation rule, which is the first one on this slide. And in the same way, we have a computation rule for the universal quantifier. So here you see that the function proof, which is an injective morphism, but not a surjective one, is the Curie-Howard isomorphism. It takes a proposition, it yields a type, and the fact that we have stated the first computation rule expresses that the proofs of an implication are the function mapping the proofs of the antecedent to the proofs of the succedent. So the Curie-Howard isomorphism is not here just a general idea that we use to build the formalism. It is a particular symbol in this formalism, whether you want to have this isomorphism or this injective morphism or not is a matter of choice. If you want to have this morphism, you just take this symbol. If you don't, you don't. Well, if you want now to express proofs in predicate logic, as Johan Gerand did with the proofs of Euclid's element, you know enough and you can stop listening. But maybe you want to express stronger theories, such as simple type theory, which is implemented in Hall 4, in Hall Light, in Isabelle Hall, and so on. And in simple type theory, compared to a predicate logic, you just have two more features. The first one is that propositions are objects. And to have propositions as objects, the only thing you need to do is to introduce a name for the type prop. And this is what we do here with the constant omicron. And then you need to introduce a way to build functions and types for functions within the theory. And this is what we do with this arrow that maps two sets to another set, that is to names of types to another type, to another name of type. And here you see the name of constants and rewrite rules that we have defined in Deducti. And if you start from the center of the picture, you will recognize the symbol that we have discussed together today: iota, set, lowercase iota, element, prop, proof, for all, implication. And then on the west of the picture, you find omicron and the arrow of types that are needed to extend predicate logic to a simple type theory. On the north of the picture, you see that we can introduce more symbols and more rules. First, for the constructive conjunction, disjunction, and so on, so the constructive connectives. And then at the top north, you have the symbols that you have to introduce if you want to express classical proofs. So here we see the trace of ecumenical logics in Deducti. We have the possibility to express both constructive and classical connectives. If you look at the south, you see some symbols that are used to express polymorphism, because we do have polymorphism in some implementations of simple type theory. So what is really implemented in Hall Light, Isabelle, and so on, is in fact an extension of simple type theory with polymorphism. What we have on the southwest is a symbol that you need to express predicate subtyping, hence proofs coming from the PVS system. PVS is an extension of simple type theory with predicate subtyping. And if you look at the pink part of the picture, where you remove the non-dependent arrow that we have in simple type theory, and you replace it with a dependent arrow, which is completely on the east of the picture. And in the same way, you remove the non-dependent implication and you introduce a dependent implication. You get in pink the calculus of constructions expressed in Deducti, and this is what we use to express the proofs coming from Coq. So you see that you don't need to take all these axioms. You can pick the axioms according to your taste. If you just want to express proofs in minimal logic, you just take what is at the center. If you want to have dependency, you take what is on the west. If you, I think I forgot, I mistook east and west, but you understood what I meant. If you want to have polymorphism, you take the axiom for polymorphism. If you don't, you don't. And you can really customize the theory that you want. So these axioms are enough to express predicate logic, as we have seen. Also, simple type theory. I just gave a few hints here. Also, simple type theory with predicate subtyping, simple type theory with polymorphism, the calculus of constructions. So almost all the theories that are implemented in modern proof systems. Of course, the reality is a little bit more complex than what I'm saying in this talk, but this is the take-home message. Of course, we can introduce more symbols for universes, universe, polymorphism, predicativity, inductive types, and so on. And also for more advanced versions of type theory, or even for set theory. And you see here the works that you should refer to if you want to learn more about it. And to conclude, I would like to discuss a little bit with you the benefits of universality. So why should we care so much about the universality of mathematical truth? So first, it is a key to be able to reverse engineer proofs. So I already told you that we had the first book of Euclid's Element in Coq, and now we have the same proofs in predicate logic. In the same way, François Thiré took a proof of Fermat's little theorem developed in Matita. Matita is just a system which is very close to Coq. It's a little brother of Coq. And he explained how to translate these proofs to simple type theory, which is much weaker. And also, Tiago Felicissimo took a proof of Bertrand's postulate. I don't know why this theorem is called the postulate, but Bertrand's theorem in Matita. And he could show that it can be expressed in predicative type theory. So now we know that Bertrand's theorem, Bertrand's postulate, holds in predicative systems.
Gilles,
yes?
I know you're getting near the end, but just letting you know we're in question time already.
Okay, so I have just 1 more minute and then I will take the question. So this reverse engineering of proof is the basis of interoperability. So we have the first book of Euclid's Element now in many systems such as Isabelle, Hall, TSTP, and so on. The same holds for Fermat's little theorem and Bertrand's postulate. And finally, it is also important so that we can cross-verify proofs. That is, we can verify proofs that have been developed with one system in another system so that we have a higher confidence. So for that, there is a social motivation. I guess that mathematicians and industrials will be more likely to use these systems if they understand that they express proofs in some theory, possibly with some axiom that they can debate, rather than in an exotic system which is just defined by its implementation. But there is also a philosophical motivation. The universality of mathematical truth has survived many crises, and we should not, and we don't need to give up on it. Here are a few ways you can contribute. We can discuss that during the questions. And now I'm ready to take questions. Thank you.
Okay, thank you. There are claps in the chat, and so we'll open it up for questions. If anyone has a question, you can unmute and ask, or you can raise your hand. I had a question in the meantime. You had a slide called making, at the top it was called like making generic. Maybe you can share your slides again.
Yeah, sure.
Yeah, something like 2/3 of the way through your slides.
Yeah, I know which slide you're talking about.
And in there, you talked about this capital iota and then lowercase, and you had this set. And I'm kind of waiting and pausing until you get there.
Yeah. Sorry.
No problem. So my question was, a little bit back. Can you go forward again? This one, yeah. What did you use capital iota? This one. What do you use capital iota for? What if I just had lowercase iota and L? Like, why do you?
Okay.
What if I just set capital iota equal to the sum over all little I of type set of elements of I?
Yeah, this is a very good remark. You can indeed do that. And if you read earlier versions of the paper, this is what we did at that time. It is just that for pedagogical reasons, it is better to introduce first capital iota here. And then when we discuss the case of the universal quantifier, we have to introduce the lowercase iota. But as soon as we introduce the lowercase iota, as you remarked, we can just drop the capital iota and use element of lowercase iota instead.
Okay.
Great. In general, if you have a rewrite rule where either the left-hand side or the right-hand side is just a constant, you can see it as a definition, and you can replace the defined symbols by the body of the definition, and you get an equivalent theory. So you can do that here, but you cannot do that there. Here, for the rule transforming a proof of X implies Y into the function, the type of the functions mapping proofs of X to proofs of Y, here, this is not a definition, and you cannot remove this rule. But the rule that I presented here, you can indeed remove it if you replace capital iota by element of lowercase iota.
Okay, great, thanks. And we have another question from Valeria.
Hi, Gilles. Thanks very much. That was extremely interesting, and one of the reasons why I kind of wanted to have you talking to us was exactly this difficulty of translating. I mean, you presented as universality of mathematics, but of course, other people, more industrial people, kind of tend to think of it as being the possibilities of translating between different systems.
Of course.
So if you could put back the beautiful, colorful picture with all the systems, I wanted to ask a question. I can see that some of the things here are implementational stuff, right? I mean, if you want to have polymorphism of this or that shape and stuff, but others are more intrinsic somehow, or at least feel to me more intrinsic. And it also kind of seems to indicate that, everyone should really agree on the minimal foundation, the thing that's in the middle, right? The very center. So, my question is, are we kind of saying that people should always, to make this ability to translate between systems, should we stay or try to stay in the middle of the picture?
Yes. Well, first, you're completely correct. We all need to agree on the symbols that are in the middle of the picture. But it's very difficult to disagree with these symbols. Of course, you will find people who disagree with them. But when we just express that we have a type for terms and a type for proposition and a type for proofs of each proposition, well, it's difficult to see why we would complain. And if you look historically, people have much more complained about what is at the periphery of the picture. For instance, adding the constant Omicron introduces impredicativity. So then we want to maybe restrict, and we can do that, restrict the use of this Omicron symbol so that we keep a predicative system. When we use the classical connectives, of course, we do have classical logic, hence some people will disagree. the need to have dependency on the west part. I should say left and right because I don't know where east and west are. On the left part of the picture, of course, there is a lot of debate. There is a lot of debate about predicate subtyping and so on. So it's true that when we want to translate proofs coming from, let's say, PVS to, let's say, HOL, then we have to remove the use of these symbols that are specific to predicate subtyping. In the same way, when we want to translate a proof coming from Coq to, let's say, whole light, then we have to remove the dependencies. So it means that sometimes it works, sometimes it doesn't. And we know that it's not the case that all Coq proofs can be translated to whole light, and it's not the case that all whole light proofs can be translated to Coq. So exactly in the same way, you could tell me there is a very nice theorem in geometry, and I want to translate it from Euclidean geometry to hyperbolic geometry. But then there are two cases: either you use the axiom of a parallel, the parallel axiom, or you don't. So if you don't, then of course you can translate the proof. But if you do, of course you will fail. The translation will fail. Our hope and our empirical evidence, although we have a limited experience, is that many proofs that are in the libraries of proof systems are similar. So even if Coq is a very powerful system, even if Lean is a very powerful system, the users of Coq or the users of Lean, they use only a part of it, a bit of it. And this is why the translation works in many cases. But of course, we should not expect to have a translation that works in all cases. We know that there are theorems that require the axiom of choice. So you cannot at the same time want the theorem and reject the axiom of choice.
Right. Yeah. No. Thank you. Thank you. I have to think a little bit more about I think the first part of the talk on the crisis kind of, I had a very different the view of it to begin with, but I like very much this picture. So I'm sorry, the southmost things. What are they?
Yeah.
Scheme and
yeah. So this is what you need to express a polymorphism on top of simple type theory. So if you take, for instance, the whole light system, John Harrison would advertise that whole light is just an implementation of simple type theory. In fact, he has a little bit of polymorphism. And this is how these 5 symbols is how we express the polymorphism of simple type theory in Deducti. And you see that if you take the calculus of construction, which is the pink square, and you add polymorphism to it, then you get the calculus of construction with one more universe. And this is the round pink part of the picture. So you see that these 5 symbols, they are used to make simple type theory and the calculus of construction polymorphic.
Maybe we could move on. Thank you for the question. We have more time for one very quick question. Dan? Oh, you're muted if you're talking. I think you are talking.
Great. Sorry about that. Yeah, thank you. So that was a great talk. I really think this is interesting work. I'm curious in practice, say as I'm a Coq user. So in practice, if I wanted to translate a proof in Coq into Deducti, there seem to be a couple of things that could make it difficult. And one being the use of tactics, and the other being the efficiency of unification and the computations that are done, they're customized in the Coq kernel to work efficiently, whereas Deducti doesn't know any meta theory about the computation rules. So how does that work in practice?
Okay, so in practice, there is a piece of software that you can download, which is called Vodka. So VO is for Coq because, as you know, VO is the extension of some Coq files. And then try to run this Vodka on your Coq files. And in the end, you get some decay files, which is the end of vodka, but also the initial of Deducti. So this is how it works in practice. Now, you don't expect to copy, to translate your proof at the tactic level. So the tactics, they produce a proof term. Then you translate the proof term to Deducti, and you should not try to read the proof term. Just like when you compile a program, you don't need to read the compiled code. You just check it. Okay. So this is for the use of tactics. So tactics are used to build the proof, not to check the proof. And now there are some efficiency issues in some cases. So this is a very awkward area of research, because the people who have worked on the efficiency of the translation, they see that in some cases Deducti is faster, and some cases Coq is faster, and we have no explanation for it. So if you can find an explanation for us, we would be very grateful. Then there are other issues. For instance, if you use Coq universes too much, then you will have to translate your proof into the calculus of construction in Deducti with universes. And if you want to stick to the calculus of construction, then you should not be too careless when you build your proof in Coq. So this is one case where the translation can fail, because you have been using universes in Coq. You have defined in Deducti a theory without universes. Of course, you can add universes in Deducti as well. But if you don't, then of course, there are some proofs for which your translation will fail.
Okay, perfect. Thank you.
Great. Thanks. Thanks for the questions, and thanks, Gilles, again.
Thank you.
So we'll stop the recording, and if anyone wants to stay on,